Dear students, distinguished teachers, professors, good evening all and welcome to the fifth session of this online summer school on quantum computing. Yesterday, Vandana ma'am, are you ready?
Yes.
Okay. Yesterday we had an opportunity to listen to Dr. Rajiv Tyagi sir. He was discussing about the Stern-Gerlach experiment and the related consequences like spin, etc. And today we have with us the speaker, Dr. Abha Khandelwal ma'am. Welcome, Abha ma'am. I also welcome Vandana ma'am, who is the host today. With these few initial remarks, I hand over the proceedings to Vandana ma'am to host the proceedings.
Thank you so much, Dr. Thank you so much, Dr. Madhusudan. A very pleasant evening to everyone. Greetings to President IAPT, Professor Ahluwalia ji, seniors from IAPT, resource persons, observers, volunteers, and participants. We are missing Dr. Kulkarni in few sessions, but definitely he will join us in the next week. We appreciate the keen interest of all the participants and everyone who is attending this session. Today, we are having yet another exciting and informative session, which is fifth in the series, as told by Dr. Madhusudan also to us. And there will be a break on Saturday and Sunday. So everyone can relax tomorrow and day after. In this week, this is going to be the last session. And we welcome today our eminent speaker for today, Dr. Abha Khandelwal. Before that, I would be giving some important announcement. I'm repeating these so that we maintain this. Keep the mics muted. You may unmute it in the question answer session after the questions asked in the chat are addressed. And please raise your hand if you wish to ask any questions. Questions can be posted in the chat, preferably towards the end of the session so that these are not missed out. If questions are not answered, please send to us on email as well. All are requested not to scribble on the screen, and all are also requested to join the WhatsApp group in case you have not yet joined. 80% attendance and participation in quiz is mandatory requirement for the certificates, and kindly attend all the forthcoming sessions on time. In case you have missed any, just compensate that by the forthcoming sessions. We are emailing and sharing in the group all these simulations and resources. Please start reading these and join the session with the registered email ID only, and also attempt the quiz only from the registered email ID. With this important announcements, I take this privilege to introduce speaker for today, Dr. Abha Khandelwal, a meritorious student throughout and a dedicated educator, hails from Orange City, Nagpur. She is a retired head of the Department of Computer Science, and she has served at Hislop College, Nagpur in the capacity for an impressive 27 years. She was associated with various academic bodies at RTM Nagpur University in Nagpur, and under her guidance, so far, 4 research scholars have successfully been awarded PhD, and she has published 30 plus international papers. Dr. Khandelwal is a passionate learner herself, and she has left an indelible mark on the field of computer science education. She is very popular among students, and she too is passionate about students. Recently, she founded a national level association of all computer science teachers, that is AACST, a testament to her dedication and vision. She has been awarded Dr. Radhakrishnan Gold Medal Award for contributing Pearl model in e-commerce optimization. Her passion lies in equipping young minds with cutting-edge technology and with a dream to make them capable of serving the nation in digital development. With these, I would request Dr. Abha, I welcome you on the behalf of the committee, ma'am, and we are eagerly waiting to listen to your talk. Please, over to you now.
Recording in progress.
Madam Abha ma'am, you might have joined from two gadgets, it seems.
Ma'am, if you disconnect from one of the, I think you have joined from two links, so you can quit from one.
You have already joined, ma'am. Please share your screen.
হ্যালো বলছি অভিরূপদা আমাকে বলছে
Everyone else is requested to mute your mics. Please do that.
Abha ma'am, you are muted. Please unmute yourself.
Is ma'am there at the moment? Ma'am is there or she has quit?
No, ma'am. Maybe.
Yeah, she may try to join again. So we
Yeah,
can
she
just
will
wait
try
for
to
2 minutes.
Yes, ma'am.
Yes. Ma'am's talk is going to be today on quantum cryptography, and that is going to be a very interesting talk. So let's wait for her to join in.
Mute myself first. Now I am audible.
Yes, ma'am.
Yes.
I am audible. Now I am. Okay, now everything is okay. Now let me share. Why I'm not able to share?
Ma'am, are you the host now? You are host. In that case, you can
No,
please share the screen.
my host. But I'm
Dr.
not.
Madhusudan, Dr. Abha is the host today, na co-host.
I made him I made her the co-host, ma'am.
Okay, I will also check it. Yeah, just a moment. Ma'am, you are the co-host, so please do join. Do share your screen, ma'am.
Okay. Is my screen visible?
Not yet, ma'am. Your screen is not yet visible.
But it is saying join, and if I join, then it will be double joined. What's wrong?
Recording in progress.
Abha, ma'am, are you there?
Yeah,
Yes,
I'm
yes,
there.
I am.
Can you hear me? I'm there. Okay, I'm getting a screen now. Chrome tab, window, entire screen. Shall I go for entire screen?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am. You can go for entire screen.
I'm going for entire screen. Okay. Now perhaps. Okay. Now, is it visible? No.
Ma'am, not yet. It has not yet started getting shared.
My screen is not shared yet.
No, ma'am.
It's not getting shared, no.
Ma'am, there is a green icon there, share screen. I think you
Yeah,
have
but
seen
share
that.
is not, it's only cancel is there. Cancel is,
Uh,
share is not
After
working.
you select your entire screen, then there must be something called OK. You can do that. And then,
Not even that working. Should I go for window? No.
ma'am, otherwise, can you email your PPT to me? I can then share on your behalf if that works.
Okay. Can I send you on WhatsApp?
Yes, ma'am. I will try to download it and then I can share on your behalf.
And in between, I'll also try.
Okay, ma'am.
Okay, I'm sharing with Dvanil.
Okay, ma'am. Okay, ma'am. Dvanil can also do it.
And can also do it, his course.
Yes, ma'am. Please do that.
Mhm. Got it, Dvanil?
Yes, ma'am.
Please share.
Habis pertama bisa pulang menang. Bener?
Dhanil, you can use slideshow mode.
Dhanil, please go to slideshow mode.
Yes, ma'am, I have done that.
No,
I think, Dhanil, it is not yet done.
no, not yet done.
Is it visible now?
Dhanil, please do it. Yes. Nice.
Yes, thank you so much, Dhanil.
Thank you, Dhanil, and sorry for the delay. I don't know
Ma'am,
what
please talk.
happened, but really sorry for that. And today's fifth session. Welcome all young participants and curious colleagues. Thanks, Professor Arvind Kulkarni, though he is not here today in the meeting. IAPT President Professor Aluwalia and organizers RC22 for giving an excellent opportunity to team up with esteemed team members, including course coordinator Professor Vandana, Dr. Rajiv, Dr. Jyoti, and Dr. Kiran. A special thanks to Professor Balakrishnan sir for his blessings. Sincere appreciation to all the participants for their curiosity they have shown and the sincerity with which they are attending the uh, speakers' speeches or the lectures. Today, let us embark on a journey into the captivating universe of quantum cryptography, where the laws of physics safeguard our digital secret. Let us begin. Next slide. Yeah. Cryptography is not a new concept. All great civilizations have developed techniques to send communications in a secured way. These civilizations also made use of secret keys. Cryptography is one of the oldest sciences and it ensures that two parties communicate safely without any interruption or without being your communication leaked. Cryptography is all about encrypting and protecting data so that only the person with the correct secret key rather, can decrypt it. It ensures confidentiality and this is done to protect sensitive information being leaked. A typical example is the messaging tool WhatsApp, which encrypts conversations between people to ensure that their messages should not get hacked or intercepted. Next slide, please. Yes.
Dr. Abha, that I think we are able to hear Dr. Lindem. Please check your at your end.
I don't know what I'm supposed to check.
No, ma'am. I was saying to one participant, he has written that he is not hearing. So I'm saying that we are able to hear. He can check on his end.
Yeah.
Thank you.
Okay. Thanks. Now, shall I continue?
Yes, ma'am. Please do.
Quantum cryptography, it differs from traditional cryptography system. And nowadays it is called as classical, the traditional cryptography is called as a classical cryptography. Physics has taken the role of mathematics. Now, blue qubit has, oh, I cannot use my mouse anyway. So, blue qubit has charted these differences. Blue qubit has charted these differences in an attractive way, and I failed to resist my temptation to put it on the slide. Classical cryptography is widely used, well established, and tested, and it is easy to use. Whereas quantum cryptography is sophisticated and still is in early stage of deployment. Classical cryptography can span millions of miles, whereas quantum cryptography has a very limited range, the most successful of which was able to distribute the key across a distance of 833.8 kilometers. Quantum cryptography requires less expenditure, whereas quantum cryptography implementation cost is very, very high. Next slide, please. In 1968, Stephen Wessner, very few know about him, from Columbia University in New York, he was the first to propose the concept. His seminal paper titled Conjugate Coding was rejected by IEEE Information Theory Society, but eventually published in 1983 in SIGAP News. A few notable researchers, quantum physicists, they developed the concept of, later on, they developed the concept of quantum cryptography. One of the key pioneers is Charles Bennett, who along with Gilles Brazet introduced the concept of quantum key distribution in their groundbreaking paper titled Quantum Cryptography, Public Key Distribution and Coin Tossing in 1984. Next slide. Let us see the principles of quantum mechanics which have contributed to give us the system which can keep our information secured for lifetime. A quantum property cannot be observed without changing or distributing it. Heisenberg's uncertainty principle gave us this property, and no cloning system said that whole particles cannot be copied. So with these properties, and after getting into the idea that the photons can transmit information, building upon this work, Bennett and Brazet in 1984 proposed a method which is named like BB84 for secure communication. Next. BB84 protocol, it uses photons to transmit data over fiber optic wire. So what is photon? A single photon, actually what is single photon? So a single photon represents a very tiny amount of light. These light waves are electromagnetic waves, and they can vibrate in different directions as they propagate through space. Now, how a single photon is generated? So drive a single atom, by the laser and excite that. Switch off the laser, and now the single atom, after some fraction of second, depending on the atomic lifetime, will emit a single photon. And nowadays, a quantum dot is on demand single photon source. Now let us learn about what is polarization. But before jumping to that, I would like to make it very clear to you that why I am taking all these, why I am telling what is photon, what is single photon, how it is generated, what is polarization and all that. Because after this, when we will be learning quantum cryptography model proposed by BB84, So that time, all these terminologies will help you to understand that model. So prior to that, if you have a clear idea about these, and something will not run in back of your mind just to think about what is photon, then how will it be generated, and then what is photon polarization, and what all ma'am is talking about. So for that purpose, I am taking this. So a quantum dot that we have already told you. Then polarization, the direction in which electric field of light wave vibrates, that is called as polarization. Photons can be oriented or polarized in a specific direction, and thus qubits can be implemented using polarization of a photon. Sorry. Go to next slide, please. Now, each photon, it can represent a qubit. Qubit means quantum bit. You have heard a lot about it, and now you are very well acquainted with qubit. So qubit is nothing but it will also hold a bit. So actually our machine understands only the language of 0 and 1, nothing else. So when we talk about the classical bits, they are 0 and 1. And when we talk about the qubits, they are also 0 and 1. Only the difference is that the qubit can hold 0, it can hold 1, and sometimes it can also hold both at the same time, 0 and 1. So if you want to if you want me to clarify you this further, then at the end, let me finish my talk, the lecture first. And after that, I can switch over to this part to give you a very clear idea about, because it looks weird when we say it is in both the state 0 and 1 at the same time. Head and tail both at the same time, then it really looks weird. But when I will tell you in terms of computer science that how it is being implemented and what actually is the meaning of being represented as head and tail at the same time, so that I can make it very clear to you, but after finishing the talk. Then, so I hope now it is clear that our quantum bit, it must have two distinct states. Why? Because we need two distinct states for representing zeros and one. So one should, whenever any basis you are taking, in that basis you should have two distinct state, and out of these two, one should represent 0 and another should represent 1. Because I have already informed you that computer doesn't understand anything apart from the language of 0 and 1. Now the polarization state of a single photon makes it possible. How? Because the photons can be polarized in a particular direction. For example, and then we can assign values to those states. So as a terminology or as a standardized thing, like horizontal and anti-diagonal. These polarized states are ascribed a logical value 0, whereas vertical and the diagonal polarized states are represented by logical value 1. So this way, a classical bit 0 or 1 is encoded into the polarization of a photon, and this, how we will achieve this? Yeah, I was telling you that polarization means it is vibrating in all possible directions. So how will we make our photon to be on a one particular state? And that is possible, that is achieved with the help of filters. A polarization filter, yeah, thank you. So a polarization filter, which is also known as polarizer, it is an optical device that selectively allows the transmission of light waves with a specific polarization oriented with a specific polarization state while blocking all other light waves with different orientation. So on the screen you can see the polarizer, thank you, Dhanil. So you can see the polarizer, right? And in this polarizer, there are two bases, horizontal, vertical, and another is diagonal. Now again, horizontal and vertical bases, they have two filters, which are the horizontal one and the vertical one. And you can see there that the horizontal one is being assigned a value 0. So physicists will say that our photon is in horizontally polarized, and computer scientists will say that it is 0. And again, when we'll talk about the vertical polarized photon, you will say it is vertically polarized. A computer scientist will say it is 1. So this is how we are able to achieve making our photon by polarizing it to give us the value as zeros and 1. Similarly with diagonal, in diagonal basis, plus 45 and minus 45, they call it as diagonal and anti-diagonal. If it is diagonal, then assigned value, logic value 1, and if it is anti-diagonal, then it is 0. Same is depicted below with the angular, 45 and all that. So the Baby 84 protocol model uses 4 polarization states. So if something is going in your mind that why only 2 bases, HV and diagonal, it is Baby 84 protocol model. It has used 4 polarization states. So we are binded with these: vertical, horizontal, 45 degrees right, 45 degrees left. Now, horizontal and vertical orientations are linear polarization states, and so are diagonal states. So all of them are linear polarization. In 1992, 6 years after this model, Charles Bennett, out of the two, one was Charles Bennett, I hope you remember, he presented a new quantum key distribution protocol and named by his surname and the year that was published. So the protocol is essentially a variant of BB84 protocol, with the main difference being that B92 uses 2 states of polarization instead of 4 that are being used in BB84 protocol. And along with its architecture, that an eavesdropper can be detected. So that care is being taken in that also. So next slide. So before jumping to this again, okay, let us switch over to this. These photons are polar. Now this is clear to everyone that these photons are polarized with respective polarizers or respective filters. Now polarized photons, they are transmitted to receiver. They are transmitted to receiver. The sender has sent photons, polarized photons, and they are being transmitted to receiver over fiber optic cables, one by one. At the receiving end, there are 2 beam splitters. A beam splitter creates a quantum superposition. And you know it very well. Day before yesterday in that session, how to create a quantum superposition using a beam splitter, you have seen. You have been given knowledge about it. So now you don't have any difficulty in understanding this, that a beam splitter does create quantum superposition. Now then there is a photon detector which will measure or which will detect its for mapping their state. Now mapping means with which it will map, definitely bit value 0 or 1. So whichever the photon with whichever state it will reach to will go to the detector. No one knows in superposition. No one knows that they have repeatedly you have been being made aware of that in superposition state, whether it will be had or tail, no one knows. So same thing will happen here in superposition. At the receiving end, the receiver doesn't know whether he is going to receive 0 or 1. Whatever will we at that particular moment of time, so that will be detected by the detector. And before collapsing, photon is in superposition state, and therefore the result is uncertain till it collapses. Now, when does it collapse? Okay, so please skip these next two slides. No, just come to before this. Move back. No, just one more. Go back. Dhanil, again go back. Okay, perhaps you were here and I forgot. Anyway, we have created and detected. Okay, this is over now. Now please jump to that. So with this, no, okay, next, and then next. Thank you. So now with all this knowledge, now we are going to demystify that how the quantum cryptography model works, and that too BB84. Now this model was proposed in 1984 by Bennett and Brazzard, and that's why the name. The idea was to encode every bit of secret key, because what is a secret key? It is nothing but it is a sequence of zeros and one. Now, all this, the idea was that every bit they should be able to encode into the polarization state of a single photon. The protocol then runs as follows. Now they have taken BB84 protocol itself, their model itself has taken, perhaps for making it more interesting, they could have taken it as sender and receiver, but instead of that, they've taken two virtual persons, Alice and Bob. And here Alice is the sender and Bob is the receiver. So whenever I call Alice, sorry, and then the Alice is nothing but sender, and whenever I use the name Bob, that means Bob is receiver. Now Alice sends a sequence of pulses, each of which ideally contain single photon polarized differently. So this, yeah, very nice, Dhanil. Thank you so much. Wow, interesting. So Alice encodes zeros in horizontal polarized photon. Now it is up to Alice that what bit sequence she has to take, and just point on the Alice bit sequence. So it is 1 0 1 1 down in the table. 1 0 1 1 0 0 1 1 0 0 1 1 1 0. Who decided this? Alice. She wants to send this as a secret key. This sequence, bit sequence, as a secret key. Now, what happens? Alice has encoded zeros into horizontal photons, right? Horizontal is always 0 and vertical means it is 1. So horizontal polarized photons, that is 3, she has given polarized, H polarized, and then she has encoded 4 into V polarized photons. So you can see there is a balance. But there are 14 photons have been sent. So what happens? Only half of the cases. This is only half of the cases, and the other half of the bits then randomly are again encoded using a diagonal polarization. Now, diagonal polarization basis is again in that diagonally polarized 4, and she has anti-diagonally polarized 3. So generally it is balanced way of polarizing the photons between the two bases they have taken, and again in two bases there are two states, so there are 4 total states. Out of 4, 2 belongs to 1 and 2 belongs to, remaining 2 belongs to 0. Now what happens, you can see, please show, they are traveling, all the photons are traveling. So this is the last one, and now this is the first one. So they are traveling and they are reaching to Bob. Just show them Bob, yeah. So Bob is there. Now Bob, the receiver Bob, it uses beam splitters of his choice randomly using a standard setup, but he is free to choose any splitter. So there are two beam splitters. One is diagonal beam splitter and another one is horizontal vertical, which in short is called as HV.
Madam, what is the logic that 0 and 1 are assigned? How they are assigned? I couldn't understand. This 0, 1, 0, 1, how they are assigned to
Sir,
the
the terminology which they have taken is that it is universal, that vertical will be taken as 1, and when vertical is 1, horizontal will become 0. And
Zero.
diagonal, if it is treated as 1, so this will be 1, the other anti-diagonal will become 0. So this is how they have
diagonal
decided.
is 1, the diagonal,
Diagonal
anti-diagonal
is
is
1. If it is diagonal basis, then diagonal will be 1 and anti-diagonal will become 0.
0. Okay.
Yeah. And if it is HV, in that case, the vertical,
is-
because
oh,
I
it
said
is
if I
convention.
do this, that means it is 1. So just remember vertical as 1 and then horizontal as 0. So now, where were we? Yes, I got lost. I think we have discussed about the bob. No? Bob is, there are two beam splitters, diagonal and horizontal and vertical beam splitters. Now Bob has freedom to choose because he doesn't know which bases were used by the Alice. Which bases Alice has used, Bob doesn't know. So what Bob will do, according to his choice, randomly, he will fix, and then he will decide that this particular photon is to be received by diagonal beam splitter or HV. So it is up to his choice, and then they will be received by the photon detectors. Now, the detectors are used that to distinguish between H and V and the diagonal and anti-diagonal state, because detector will whichever state will reach to the detector, then detector will give the measurement will be either 0 or 1. So HV will take vertical as 1 and horizontal as 0, and our diagonal beam splitter will take diagonal as 1 and anti-diagonal with 0. So this is how the values will be measured. Once photons are detected and the measurement is done, they get destroyed. So Bob then publicly announces that which basis he used for each bit. Then Alice then confirms that in which cases they use the same basis. And they throw out all the bits which they have used with different bases and leave only those where they use the same one. After this procedure, the length of the key, the shifting key, which Alice has sent, will get reduced, and but it remains whatever will remain, which will coincide for Alice and Alice and Bob both. And then they check if there was any eavesdropping, and if any doubt, then the whole key is thrown and the procedure is repeated. Now, the table below, just show the table. Just show the table. The table below gives an example of transmitting 14 bits of secret key, and after the key shifting only, you can count 9 bits are left. Now, I will just summarize this. I mean, the key points only. The very key points which we should understand completely at this particular level, that the intrinsic randomness of the quantum states and their measurement provides the randomness in creation of the key. And moreover, QKD exploits no cloning theorem, where quantum states cannot be cloned, they cannot be copied. So we have a unique key. And furthermore, the uncertainty principle that is presented by German physicist Heisenberg make the quantum key distribution process strong against any interception or retransmission attempt by the eavesdropper. how that we will see later. So please go to, let us solve this, that how they have got the shifted key. So we'll solve with the same example also, but prior to that, I would like to make one point clear to you. So please go to next problem solving. Now let us see how the shifted key is created. Now in this example, the Alice basis was HV plus minus 45, same. And in that time, in previously, the researchers used to show this HV state, if it is one or it is vertical, then with upper arrow, the upper arrow one. And if it is 0, then down arrow. And if it is plus 45, that is 1, then it is right arrow, and for 0, negative side. I mean the reverse arrow, backward arrow. So using this concept, later on we will switch over to the whatever is being used today. So even if with this, if you want to, let's try that Alice basis, we know states are given, and what will be the bit value that you can compute. The state is vertical, bit value will be 1, then 0, y0 because y0 because downwards means it is horizontal. This is how they were showing. And then in third case, it is backward arrow 0, which is anti-diagonal. Forward.
Ma'am, what is the role of shifted key? Please explain the shifted key.
Sir, I am telling you, I will come to that.
Okay.
पहले बना तो ले. Let's create secret key, sir. Then we will see what is the use of why बना के इतना पढ़ के, and after creating secret key, what is the use? That we are going to solve that how to use secret key. So that we are going to do. So please, sir. Okay. So this way 1 0 0 1 1. These are the bit values which Alice has sent. And now Bob, as I told you that Bob has a freedom, even Alice has a freedom. She has decided all this 5 1 0 0 1 1 sequence being decided by Alice. And now Bob is receiving first photon received by HV beam splitter, second by plus minus 45 D again HV. And now these states, because of superposition, no one knows. The detector will now detector is got that in first case it is upward arrow, that means the bit value 1, the measurement will come as 1. If it is right arrow and the diagonal is there, again 1, backward arrow and it is D, then it is 0, it is HV, and down arrow, that means this is horizontal 0, and again the last one 0. So what he received is 11000. Now what they will do, they will disclose. Bob will disclose to Alice that these are the I have used, and Alice will say I have used these bases. And now they will match their bases. So now try to match. What happens in first case? 1 with HV basis, again it is being received in the same fashion. So 1 will be retained. And then what about HV and plus minus 45? This will be discarded. First will be retained, second will be discarded, third will be retained because everything is same, and fourth and fifth will again be discarded. So your shifted key will become 1 0. So out of 5, 2 it has been reduced to 2, shifted key 1 0. Now next slide, please. Now here I have taken the, yes. In this case, actually, it is the same picture, but let us try to see what is the shifted key in this case. Now we know this is the bit sequence, you know the Alice bit sequence, which is 1 0 1 1 0 0 1 1 0 0 1 1 1 0. Now for because the school students are also there, for young participants actually, I have made this table out of this only. So in this table, the polarizers are now polarizers are represented like this. If it is HV polarizer and the depolarizer. So HV, let's go here. Okay, wait, without a pointer. Okay, I will try. Now LS bit sequence you know very well. So let us write LS bit sequence first. So please come to LS bit sequence. Yeah, same I have copied. Okay. Now from where I got these states. So states I have copied. How I have copied? So you can see double arrow. Now they have used the concept of double arrow. So double arrow means vertical is shown as vertical. That means 1. Well, will carry value 1. Horizontal is horizontally clear cut. They have showed that this is in horizontal position. And then for diagonal, it is like this. Okay, oh, mirror image. So like this, and for anti, it is in other direction. So I hope you got it. In this also, yes. Please show. Can you show filters? Oh, it's working. Okay. So now, what happens? This is our polarizer. The 4 filters are there, and Alice has sent this sequence. What I have done is, this is vertical. Vertical means always HV, and HV is shown as plus. Okay. And this is horizontal. Horizontal is 0, and again, okay. So this is horizontal, and that's why I've taken this as 0. Then this is 1. This is 1. And the next one is again 0. Then next one is 0. And then comes 1. Again 1. And then 0, 0, 1. This is also diagonal 1. And this is diagonal 1. And this is 0. The last one is the first one actually is horizontal. Now this was the LS bit sequence and the Bob's detection. Now Bob has applied these filters. Now show what Bob has applied. Now please show what Bob has applied. Yes. Now Bob has applied HV. As you can see in this, from this diagram only I have taken. Bob has applied HV. After that, diagonal, then HV, diagonal, diagonal, HV, diagonal, HV, diagonal, diagonal, HV, HV. Okay. So I just copied it, Bob, so that you can clearly see it. Now Bob has applied this, and he doesn't know what will be the measurement because photons are in superposition. So what will reach to the detector is unknown to Bob, and he has got this measurement 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0. So this is assumption. This is purely assumption. We have assumed that Bob's detection was like this, and what after measurement Bob got this. Now they both Alice and Bob, they will tally their sequences. Now while tallying, now see what happens. How shifted key is made. Can you please unmute yourself, Dhanil? Dhanil?
Yes, ma'am. Am I audible, ma'am?
Yes, you are audible. So please help me. How the shifted key will be made in first case? It is HV vertical, and at the detection time also it is HV basis and it is vertical 1. So it tallies totally and therefore 1 will come there. In second case, can you please explain in second case?
Ma'am, in Alice case, it is HV horizontal, but in Bob's case, it is diagonal.
Diagonal, so it will be discarded.
Discard.
Discarded. Shifted key will be dashed there. Okay. So this way it will go on, and then at last we okay. Let us take one more example. Third one. In that case, the polarizer is D
In
plus 45, and Bob's detection he has applied which beam splitter HV. So plus is HV and cross is diagonal. So Bob's measurement will be 0. So this is what Bob has got. Okay. So because the bases themselves are not telling, so definitely they will be discarded. Now one case where it has been accepted, take to any other case. Second cell, the bit value is matching where? Yes, the bit value is matching, but the bases are different. This is HV and this is diagonal. So if basis is different, they are discarded. The bases are different. If the Alice has used HV and Bob has applied diagonal splitter for them. So they are mismatching, and therefore, although they have same value, eigenvalue is same 0, 0, but they will be discarded because here they mismatch. So the in totality, they should match. In the first case, you can see that the HV polarization is there, and then here it is plus. That means here also HV. So therefore, they are aligning and compatibility is there, and therefore it will become one of the part of sequence secret key. So this way, we have seen that the shifted key is 1 1 0 0 1 0 0 1 0. So let us try one. Next slide. As a homework, and not as a homework, here itself we will try to evaluate. Now, unfortunately, I will not be able to write. No. You will have to write then. Okay. Dhanil, please go to back to normal mode. And yes, now please, because then only you will be able to write. Nahi. This is presentation mode. Go back to normal mode. Go to normal mode. In presentation mode, you won't be able to write now. Yes, come to this slide. Yes, thank you. And put your cursor there at the first place. And you can unmute few of the participants, young participants. Let's try to evaluate. And please, Dhanil, you unmute yourself also. Yeah. And one or two who are interested. Okay, so let's go ahead. So what will be the compatibility in first case?
as the bases are not matching, it will be dash.
As the cases are not
Not
matching, it
matching.
will be dash, yes. Second case,
Both are matching, so it will be
both
1.
are matching, it will be 1. So please write.
In the third case, the bases are not matching, so it will be dash.
Yes.
In the fourth case, both are matching, so it will be 0 here.
0, yes.
In here, also both are matching, so it will be 0.
0.
In here, also both are matching, so it will be 1. In here, the bases are not matching as well as the values are not matching, so it will be dash.
Discarded, yes.
In here, the bases are not matching, so it will be discarded. In here, both of them are matching, the state and the bases, so it will be 1. In here, the bases are not same, so it will be dash. In here, both are same, so it will be 1. And here also both are same, so it will be 0. So the shifted
Please
key
check the key will be 1001110. So did you get the same?
Yes, ma'am.
Okay, then shall we move ahead?
Yes.
Wait, 100, yeah, very good. 1001, no, you are missing 1. Anyways, so you have understood that how the shifted key will be created. Now, let's move ahead. And here is the answer, sir, that how we are going to implement it, where we are going to use it, where we are going to use this secret key, which we have created using quantum key distribution model BB84. Now, first of all, let me give you some idea about the one-time pad. This is a classical cryptography scheme, and in this cryptography, the one-time pad is unbreakable classical encryption technique. It cannot be cracked theoretically and guarantees perfect secrecy, but it requires the use of one single-use pre-shared key that is larger than or equal to the size of the message being shared. Now, pre-shared key that is larger than or equal to the size of the message which you are going to send, it should be both with the sender and the receiver. Now, one-time pad crypto system, it was first proposed in 1882 yes, to preserve confidentiality of telegraphic messages. It uses a pre-shared key that its size must be the same as bigger of the message or bigger than the size of the message. And in this scheme, every key is used only once, and that is why it is called as one-time pad. Now, quantum key distribution helps to create these super secret keys which we need for a one-time pad to encrypt messages. So it's like having a super secret code that is extra safe. Because there are several methods. You can even go for head and tail, and sender and receiver, they can just make a secret key. They can decide that secret key like this. And previously they used to decide like this only, and using some other methods. But by using quantum cryptography technique, if you are manufacturing, I can say, or if you are creating a secret key, and this is being utilized for one-time pad, so then your key is, it is your super secret key, which cannot be hacked anytime. Now, key points are that it requires a random key that is at least as long as the message. Not that in particular sequence you should have a key. It can be any random sequence of 0 and 1 and should be as long as the message which is being encrypted, and encrypts by performing a bitwise XOR. So already you have been given the knowledge of bitwise XOR in previous sessions by Dr. Vandana, that now we are going to use this bitwise XOR operation between the messages, the plain text and the key. And then this ciphertext is sent to the receiver, and the decryption also involves another bitwise XOR key with the same secret key. So this is how we are going to use the one-time pad. And prior to that, yes. Oh, okay, let's go ahead. Next slide. Yeah. Now, for designing a key, you have to take a sequence of 0101. Actually, most of you must be familiar with this. These are the ASCII codes. There is ASCII code for every character. Whichever you press on your keyboard, for each and every character, there is a ASCII code. And some ASCII codes are assigned to even these characters A to Z. So for simplicity, we have taken these characters. Now, these are the binary codes 0, 1, 0, 0, 0, 0, 0, 1. These are the binary codes, so you cannot write A in your machine cannot understand A as A. Only human being can understand A as A. The machine only knows the machine language, which is nothing but a sequence of 0 and 1. So if you are writing this sequence, the first one, and then it will say that A is being entered, the character A. It will read this as a character A and so on. Now, because my young participants are there, I would go further just to explain them that how X key value will be computed with this. So these are standard tables. Go to next. Next slide, please. Yes. So here, this is ASCII is American Standard Code for Information Interchange, and for A it is 65. Let's see how. So first of all, you will have to convert your binary number, which we have seen in the table. This was the binary number for A. So it was to the base 2 and convert this into decimal number. So the conversion is very easy. If the binary number is there, then you have to multiply each digit from MSB to LSB with reducing the power of the base number 2. So because there are 8 bits and we always start with 0, so first of all, it will be the weightage will be 2 to the power 7. So the 0 will be multiplied by 2 to the power 7. Then plus next bit is 1. 1 will be multiplied by 2 to the power 6. Then rest of them are 0. So 0 into 2 to the power 5, 4, 3, 2. And the even, okay, 2 to the power 1 is also 0. Then the last will be plus 1 because the bit is 1. This will be multiplied by 2 to the power 0. So 2 to the power 0 is always 1 and 1 multiplied by 1. So the last will be 1. And all others which are being multiplied by 0, they will be 0 only. And the only one is remaining. What is that? 2 to the power 6. So this is 64. So 64 plus 1, that is 65. So this is how the A is represented by 65. In decimal digits, it is 65. The value is that. Now, quick method. Quick method means once you become expert who is going to do all these calculations, we know that once we become matured, then there are methods. So what you can do is the first weightage pe jana, please. Go to weightage. The first weightage from left से आ जाओ, left not from right, left to right आना, last वाले पे आ जाओ, one पे, okay. So weightage पहले का 1, then 2, then 2 2s are 4, 4 2s are 8, 8 2s are 16, 32, 64, 128. Now let's compute A का. So where there is 0, you need to worry. बाकी जहाँ जहाँ 1 था, so 1 was at अगर मैं right to left ले रही हूँ, then it is from second, and then the 8th bit is 1. So 64 plus, sorry, one more. Anna, we are trying to quick method. Sorry. Fine, I will explain this and then you can compute this. So 64 plus 1, that will be 65. बाकी सब तो 0 है. Now quickly you find the value of what will be the ASCII code of Z. So please, Dhanil, unmute yourself and.
So the binary is 010111010. So if we use the quick method, then from right, so 2, this is 0, so this won't be counted. So 2 into 1, so here we write, this 0 won't be counted. So 2 into 8, 1 into 8, which is 2 raised to 3. So this is 8 here. Then 2 raised to 4, which is 16 here. Then 0, so won't be counted. And 1. So 1 into 64, which is here. Adding it is 90. That would be the ASCII value of Z.
Right. Thank you so much. So this is how quickly we can do so. Now, okay, so now let's go to our next. Yeah. Now here we will start sending message, and we will use our secret key. We have learned how a secret key can be prepared using BB84 model, and we will be using it here. And this is all assumption that what message we will send, so that we will assume, and we will also assume some secret key, and we will go further. So first of all, suppose the original message is org. Okay, so wherever org is written, this is your original message, and where key is written, this is your secret key, and where MSG is written, so that message is the message which you are sending, the message which you are sending. So this message will be received. Yes. So just recollect your truth table for XOR. You have already been, you know it very well. So in one of the previous session, we have used this, and that's why all these gates are important, and they will be using as and when they are being, they are being needed. So the message org, which can be stored in L-bit register, and let's assume that for simplicity, our L-bit register, it can accommodate, or it can hold 8 bit. So L-bit register is encoded with the use of key, KEY, which is also a number between 0 to 2 to the power L minus 1. So why is it 2 to the power L minus 1? Because we are starting with 0, so we are subtracting the first, then 2 to the power L. So the total, yes, the encoded message is nothing but, what will be the encoded message? We have already seen that what we will do, we will take our original message and we will encrypt it with the help of the secret key. So you will perform XOR operation here for this original with XOR with your key, and the message equals to, XOR key. Now what is message? Message is nothing but the original message XOR key, and again this will be XORed with another key by the receiver. So when it is being XORed, you know that, and that day also Madam pointed out very clearly that if the bits are same, then the value is 0. So 1 will be 1 XOR 1 will be 0, 0 XOR 1, 0 XOR 0 will also be 0. And if they are dissimilar, then only they will result in 1. So same will happen here, because the key holds the same values, and if they are XORed, so definitely you are going to get the answer as 0, and therefore you will get the original. Now let's take one example. Let's send a message original to the receiver in binary. And for simplicity, I've taken it as U, because U is very nice. Coding is there, 01010101. So let us send U to the receiver. Now next slide. Now, before parting ways, you and your friend, suppose you are sending it to your friend, and then you have agreed on a key, maybe using a coin with heads as 0 and tail as 1, or vice versa, and randomly you have generated a key of the same length as of message, and both have made sure that they have the same key. This is very important. Now here is a twist. Using QKD, both of you have obtained the key instead of using head on tail or any other classical method. You have obtained it using the QKD, that is quantum key distribution method, and by applying BB84 protocol. Now let us assume that our shared key is following. For simplicity, again I have taken it as 11110000, and now perform XOR or exclusive or operation between, sorry. So this is just, I've already informed you, same bits means 0. So go to next slide now. Okay. Now our encoded message is original XOR key. Your original message was, yeah, please unmute, Dhanil. Original message was,
Original message was 01010101.
yes,
That is
and
you.
key was, yeah, ORG.
11110000.
Right. Now you compute.
As these two are different, they will be 1. As these two are same, the XOR will be 0. These two are different, so 1. These two are same, so 0. These two are same, so 0. These two are different, so 1. These two are same, so 0. And these two are different, so 1.
Okay. Now this ciphered text we will send to our friend. Okay. Now I have written Bob. Now assume Bob is your friend. So send it to Bob. Now at Bob's end or your friend's end, the decoding will be done. You have encrypted and decryption will take place. You have done encoding. It will be decoded there. So how will it be decoded? The message will, again the same key will be applied. Same key will be applied. Then apply it. The message received was 10100101, and our key is 11110000. Now again perform this.
These two are same, so it will be 0. These two are different, so it will be 1. These two are same, so it will be 0. These two are different, so 1. Same, so 0. Different, so 1. Same, so 0. And different, so 1.
So what is this 01010101? This will be the message received by your friend. And what will be it? It will
It
be
is you, the
it
original
is
message.
you. The original message, you. So this is how the one-time pad is used along with the quantum cryptography, the key generated by quantum cryptography method. Now next. Now let us see what is the eavesdropper, what eavesdropper will do. Now eavesdropper is there, but suppose the name of they have taken it. EVE is the name given by the model, those who have designed the model. Now it tries to eavesdrop and to measure each of the Alice photon. But the moment she tries to confirm, suppose she has measured all of them instead of Bob, she has carried out everything and she has everything in hand. But as soon as she tries to confirm it with Alice, she will get exposed, right? And the next, photons, they have Heisenberg uncertainty principle that photons will get destroyed once they are measured or they are tempered. So because of that, once it hits a detector, the photon will no longer exist, and whichever the Eve will try to detect, so they will get destroyed, and Bob will receive less photons as was expected. So as per expectation, it is assumed that at least 25% of transmitted photons, because we have not talked about them because it will confuse while understanding the methodology, but few of the photons will definitely will get destroyed because of the environment and the noise and all that. So 25% of the total transmitted photons must reach to the bomb. So if we get less traffic, then definitely he will guess that something is wrong in the system, and this is how they will throw and will go for creating another one. So why quantum cryptography is secured, we have discussed it very nicely. I think now it is very clear because of these two properties provided by the quantum mechanics. We the quantum cryptography is totally, it gives a secured method for say for sending our messages in a very safe way. Now, next slide. Now, let us summarize. So, first of all, I would like you to read all the three slides one by one. And after that, I will proceed further. So, please be attentive and just try to understand each and everything and see if you have understood it or not. All the young participants, please read them very carefully and very attentively. So, I'm giving you some time, and as soon as you finish this slide, please give a green signal in chat so that Dhanil will go to next slide. Dhanil, next slide. Next, please.
இங்க வரேன். நீ சாப்பிட்ரு, நீ சாப்பிட்டுன்றது முடி போறது, நீ சாப்பிட்டு.
Okay. So, there was a question that how both will get the same key. So, this is what we were doing with that methodology. It is only because for designing a key, for preparing a key which is known to Alice and Bob and no one else. So that method is for that purpose only. So yes. Now okay. Next. Okay. So now, why there is a growing demand for quantum safe solutions? So because yes. So I'm not getting. We will discuss all the. Just we are going to finish, and then we will take all the in question answer session. We can discuss everything. So shall I go ahead?
Yes, ma'am, please.
Okay. So, because the world is anticipating that the quantum computers, they are capable of breaking traditional encryption, and therefore the demand for quantum safe solutions like quantum cryptography is set to skyrocket. Because even when quantum computers will be there, even that time the classical computers will also be there, and then the key generated using quantum cryptography methodology will provide the solution to the classical computers to keep themselves safe from the attack from even from the quantum computers. And for that the post quantum cryptography is there. So latest research area is that. And quantum cryptography, because the principles of quantum mechanics are being utilized here instead of mathematics. So it holds immense potential for revolution, for changing the various aspects of our daily lives. And it is still in the early stage of development and deployment that we have already discussed. So there are several real world applications where we do need quantum cryptography to be explored and implemented. So let's go through a few of them. The secure communication networks. So all new applications such as quantum digital signatures will come, and quantum secret sharing and quantum voting. So they can enhance the functionality and trustworthiness of all the cryptographic protocols. Now on this platform, I have already written, but I have one novel idea. I have a dream that we should have quantum voting booths in future. We can have, and as and when the voter press the key, the vote should get deposited and recorded in the database at the central servers through 100% secured communication network. And then the results will get declared very next morning, because quantum computers will be handling all the tasks. So they are so very fast that the next day morning all the results can be declared. Looks achievable with quantum computing because it offers tremendous speed and it also offers 100% security. So we can dream like this. Then applications. Financial institutions, there is sensitive data and secure transactions should take place. So definitely their financial services, their quantum cryptography will play a major role. And data centers and cloud computing, they handle vast amount of data, and it can play a significant role there also to secure all these infrastructures. And then the Internet of Things. Now, Internet of Things, IoT devices, they raises concern regarding their security to cyber attacks. The quantum cryptography offers a potential solution by providing a secure key distribution and encryption mechanisms for IoT devices with quantum resistant algorithms, secure communication channels the integrity and confidentiality of IoT data, it can be preserved, saving us from potential risk. Then in defense, of course, in defense, the quantum cryptography, it can enhance the government and defense organizations' capabilities by enabling the secure transmission of classified information, protecting the military information communications, which should be which are of vital importance, and they are very critical and they should be totally secured. So the integrity of critical infrastructure can be ensured using quantum cryptography. Healthcare and medical data, there also there is a vast application of quantum cryptography, because the sensitive patient's information, medical records, there is a need for additional layer of security to be provided for protecting electronic health records. And then it can enhance the authentication and identify management systems also. So the query is that, is it already in end user's hand? Quantum cryptography is still in early stage of development and not widely available to end users in its purest form, but the technology is primarily being researched and tested by academic institutions, government organizations, and selected industry players. You know who are they? First day we came to know about all that. So, however, there have been some limited deployment of quantum cryptography and certain applications, but it is not yet accessible for average end user. It is still evolving and there are challenges to address. So which are the challenges? The technical complexity, because it requires specialized infrastructure and these systems are currently expensive and not easily scalable. Quantum computing development, researchers are actively working on I've already informed you, that they are working on post-quantum cryptography, which focuses on developing encryption methods that can withstand attacks on classical computers from quantum computers. And infrastructures and standards, this is again a challenging factor. Establishing infrastructure and standardized protocols for quantum cryptography is essential for its widespread adoption and to ensure compatibility between different quantum cryptography systems. So that is also there to worry about or to be taken care about. And then integrating quantum cryptography with existing communication systems, it can be challenging. It requires modifications to existing infrastructure protocols to accommodate the unique feature of quantum cryptography, and the education and awareness, which is the most important, and we people are there for it. Quantum cryptography is highly specialized field, and there is a need for education and awareness among professionals, decision makers, and users. And despite of the fact that quantum key protocols are theoretically well structured and designed, their real implementation has certain imperfections. This is human error, defective optical fibers, unwell constructed detectors, and other loopholes becomes the cause of attacks that are performed against QKD schemes. So there are various challenges that appear and are subject of research. But despite these challenges, the future outlook for quantum cryptography is definitely promising. And there is lot of scope for young generation to get into it and become pioneer in this particular field of quantum computing. And for that, what basically is needed, your math should be sound, and if you have very good in physics and computer science, then world is all yours. So with that, I end my session, and the references are there. Thank you. Thank you for
Thank you so much, Dr. Haba, for such a lucid representation. You touched upon distinction between the classical to the quantum cryptography, moving on to polarization states which are required for the bits. And then you talked about the case studies, like how these are actually done, along with the utility of the keys which are there. And then you also talked about different other examples and applications and challenges. I think this session has also provided another, say, understanding of a very difficult topic otherwise. There are some questions in the chat which I would be reading, and in that case, please keep on answering that. Vinayak says, ma'am, is it anti-diagonal? What is anti-diagonal polarization? I assume, Vinayak, by now you must have understood, because ma'am, after you had written this question, ma'am had explained again also. Ma'am, please, you can tell the answer otherwise.
If you want to understand it like this, the qubits are either in one of the two eigenstates of either rectilinear 0 or 90 degrees, or diagonal 45 or 135 degrees. So if you do not like the word anti-diagonal, it can be 135, because if it is measured from 0, then 45 is your, in diagonal case, it is 1, and then the anti-diagonal will be at 135. So that 135 degrees, and that will be counted as 0.
Germany says that,
So
what is
these
the
are
difference?
yeah.
Ma'am, please continue. Sorry to,
And then
please
it's
continue.
over. It's over.
Germany says, what is difference between a photon and a polarized photon? What does polarization do to a photon?
I think you should answer this. Why we are polarizing a photon? Because we want to align them in particular specific direction. So for that purpose, that is the difference. No? If polarized means all possible directions. But if it is polarized in one particular, like if you are sending it through vertical filter, then the state will be vertical only. So it will be in one particular direction, and then only you will be able to, or the computer scientist thought like this, and then they can assign some eigen value to eigen state. Eigen state is there, but then if we can maintain this state, then only the value can be assigned. So then it is 1. It can be assumed as 1, and then the horizontal can be assumed as 0. So that's
Ma'am, may I request you to send the quiz link, because it is being asked
yes,
in the
yeah.
chat
We will
meanwhile, so that
have,
participants can start doing it.
yeah.
And
Please do it. I've already, he shared it. I had
yes.
sent it so that they can, all
Okay,
others.
thank you. Yeah, it has been shared by Dhanil. So please, all of you can attempt doing the quiz meanwhile. I must also tell here, Dr. Abha, that for the participants, that polarizers are used in order to create different polarization states. These are polarizing sheets which can be used to create a particular type of polarization. So those who are from the physics background can also read about that, how different polarization states are created. Now, next question is this is, I think, like a comment by Germany only. Are we inscribing data into photons to transfer information? So I think you are saying it right. Next question is, what if photons? Ma'am, please say.
Yeah. What is?
What if the photons get mixed up while traveling? The information passed would then become something like an anagram to solve.
If they get mixed up. Yes, coherence is one aspect, that it is the ability of quantum system to maintain a superposition of states without collapsing into a single state through interaction with its environment. So if they get interacted, then they will collapse, and then they will be no more in quantum state, they will be in classical state. So this property is crucial for performing quantum computation, because quantum algorithms rely on manipulating and processing information encoded in quantum states. And when a quantum system loses coherence, then it undergoes decoherence, meaning it becomes more like a classical system with well-defined states.
There was a comment by Udyan, not followed how shifted key works. I hope, Udyan, now this must be clear. After you had written, ma'am had explained later also. And there is a comment by Sujaya Saha. For forward arrow, shouldn't the basis be plus 45? I think
Forward
you
is
are
plus
referring
44, yeah. Backward is minor. That's why the later stage, the researchers started using double arrow. Single arrow
there
you're
are
talking about, right? In single arrow. Did I get
there
it?
are a few more questions, but I think it is already 8:10 and people must be waiting to just now leave it. So I think, ma'am, we can send these questions to you in the email and you can answer those and these can be submitted to the participants then. And I would recall that in the case of Caesar used to use a cryptography in which
Yeah.
every word like hello, that used to be shifted by, say, H would become K, and that is how it all started in the previous times, and now now we see a classical as well as a quantum aspect of it. So I would request now Professor Ahluwalia ji to please say about the session, and then this can be handed over back to the organizers. Thank you so much.
Thank you, Vandanji, and thank you, Professor Abha. Thank you very much. I think you have done a very tough job today, and because it was packaged in a very small time frame, so the participants will have to really work hard to appreciate each and every step which you have explained to them. I think you brought in very nicely the what you call examples that how Alice and Bob communicate with each other, and the complete quantum process was explained. I think that was the key element of this. It was for the first time that Alice and Bob appeared in our seminar. But Alice and Bob are two very important, communicators who make this look like a game, which is very difficult to appreciate right in the very beginning. And that is what has been the reason that people have been saying that quantum computation and quantum information and quantum cryptography, they are very, very tough fields. For a audience which is drawn from physics background, I think it is a wonderful first exposure which you have given. I must say that. And the way you had brought out various references for the participants to follow in future, I think that should be a great, great help. Thank you very much. You added a new dimension. Rather, today we have jumped over to what you can call the application of quantum computation in a very interesting and important field at which everybody is actually trying to gain upper hand, whether it is uh, countries like India or countries like USA or China. There is a very tough competition around. So thank you very much, Abhaji, once again. I think you are one of the key members of the group who has curated this course. So I have nothing else to say, but say that big thank you for you. Thank you.
Thank you.
Thank you so much, sir. Thank you so much. And thank you, Abaji. I hand over to Dr. Madhusudan. Thank you so much.
Thank you, Vandana ma'am, for hosting this wonderful session, quantum cryptography. I would like to thank you, Abhaji, for enlightening the audience on the topic quantum cryptography. So as it is already 8:15, with few words I would like to conclude. I would like to remind the participants once again that we have a break for 2 days, tomorrow and Sunday. We'll meet again on Monday for the 6th session. So I also would like to say that as we completed week 1, I will be posting or I will be giving the YouTube link for all the 5 sessions on Sunday because we are editing the videos. So they are of 1.5 to 2 hour duration, around 5 to 6 GB. So we are deleting the introductory part and we are keeping the session and the question answers. So we are in the editing process. We'll be uploading the 5 videos on Sunday. Then otherwise, the attendance and the participation of participants are muting themselves during the sessions and unmuting themselves in question hours, which is good. So overall, I can say a big thank you to the speaker of today, Dr. Abaji, and also the host, Dr. Vandana ma'am, for handling today's session in a skillful manner. And I also thank all the eminent participants, Professor Halwale sir, Professor Balakrishna sir, Professor Ravindra Limaye, and all the senior faculty, all the senior officials of APT and teachers, all the participants. Okay, goodbye to all for this day. See you on Monday. And today's quiz link is already posted. Try to answer the quiz. Thank you once again. Thank you one and all. See you on Monday.
Thank
Thank you
you,
so much.
Mr. Madhusudan.
Thank you, sir.
Great job.
Thank you. Thank you very much, sir. With your support, we're able to do all these things. Thank you, sir.
Thank you so much.
Yes. Thank you, one and all.